What exactly is a Fourier transform? What does it tell you about a function and how does it work? And what exactly is kSpace? And how does an MRI use kSpace to produce images? If you woke up today haunted by these questions, you're in luck. This discussion will hopefully provide some answers. Fourier transforms are absolutely everywhere. In science, engineering, and math, it is a fantastically useful and powerful tool. This video is the third installment in a small series discussing how MRI works, links to previous videos in the description for those interested, but I've tried to organize this particular lecture's content here so that it stands alone somewhat, and those in neighboring disciplines can still find it helpful. As I said in a previous video, you can't say you understand how MRI works unless you can also say you know how a Fourier transform works. So that's the purpose of this video, to get you to understand Fourier theory. And it all starts with the sinusoid, everyone's favorite wiggly function and the ubiquitous solution to a never-ending list of real-world physics and engineering problems. There's a useful property of the sinusoid that I want to leverage in our discussion today, and that is that only 3 pieces of information are needed to uniquely specify the entire function. First, we need a frequency, omega, specifying the number of wiggles within a given span of our independent variable. I'm going to use time as my independent variable to get our discussion going, so our frequency units here would be radians or cycles per second. Now, alongside the frequency, we need 2 parameters. An amplitude, specifying the sinusoid crest height, which we'll call A, and a phase, specifying a sort of shift in the sinusoid, which we'll call phi. We'll use the convention that phi equals 0 when a sinusoid crest occurs at time t equals 0. So you give me those 3 pieces of information and I know the exact value of the sinusoid across the infinite range of time t. How do I know? Because the sinusoid function has an explicit mathematical form. And perhaps you can already anticipate what that form is. Now the frequency omega can be any real number, and so has a range of -infinity to infinity. But note that the amplitude is any positive real number, and phase is any number between -pi and pi since the sinusoid repeats itself every 2 pi radians. Sure, you could have negative amplitudes, but that would be redundant here since a phase shift of pi would accomplish the same thing, so we'll stick with only positive amplitudes. Now note something cool here. If we define our parameters this way, we can actually represent our amplitude-phase combo with a single complex number. After all, complex numbers contain 2 pieces of information by design, real and imaginary, or equivalently, magnitude and phase. Drawn in the Argonne plane here, also known as the complex plane, we can use the length of the complex vector to correspond to the sinusoid amplitude, and we can use the phase to correspond to the sinusoid's phase. Recall that the real part of a complex number is just the magnitude a times cosine of phi, and the imaginary part is a times sine of phi. So by employing Euler's relation, this complex number, specifying our amplitude-phase combo, is written a times e to the I phi. Since this complex number serves the purpose of scaling and shifting our sinusoid, we call it a phasor, short for phase vector. Now let's address the question, what is the functional form of the sinusoid? Well, we're not going to use just any sinusoid function today. We're going to use the granddaddy sinusoid, the complex exponential, e to the I omega t. Notice that we get 2 sinusoids for the price of 1 here, again by Euler's relation. A real sinusoid, which I'm coloring green here, and an imaginary sinusoid in purple, which is shifted from the real part by 1/4 of a cycle or pi halves. If omega is a positive number, like I'm showing here, then the real part will lead the imaginary. If omega is a negative number, then the real part will lag the imaginary. Thus, positive and negative frequencies are distinct to a complex exponential, as opposed to regular old sines and cosines in which the distinction is ambiguous. Now here's the beauty of the complex exponential. If you want to scale the amplitude and shift the phase of the sinusoid, all you have to do is multiply e to the I omega t by a phasor, a e to the I phi. The amplitude a scales the sinusoid, and the phase in the exponent shifts the sinusoid in a single multiplication operation. Beautiful. And if you think plotting both a real and imaginary sinusoid is distracting or unnecessary, that's okay, you can just ignore one of them. It is actually common practice in many physics applications to do this, work the math with complex exponentials, then just ignore the imaginary part of the solution. To get us started, I'll also just display real functions. We'll work the math and introduce concepts with complex exponentials, but I'll only display the real part of our sinusoids for the first few slides, mostly because the animations and plots are much less crowded this way. Once we get the basic concepts down though, I'll bring the imaginary part back. So with all that discussion of the complex exponential out of the way, we can finally develop our intuition for Fourier theory. In a single sentence, Fourier theory begins with the idea that any function can be represented as a sum of sinusoid waves. Here's a function f of t, which I've drawn by specifying an output f for every possible input t. This function can also be made by adding sinusoid waves together. We'll start with this frequency, which is scaled and shifted according to a corresponding complex phasor. Then we'll add this frequency, also precisely scaled and shifted. And then we'll add all the infinite number of scaled and shifted frequencies, such that, once all accounted for, f of t has been perfectly specified no longer as an input-output function, but as a frequency function of complex phasors. Here I'll draw an f of t and a grid showing all the sinusoids which yield f of t when summed. Of course, I can only draw a finite number of frequencies on a big grid like this, so I've chosen to display the integer frequencies here, 1 Hz, 2 Hz, 3 Hz, etc. But of course, all real number frequencies will have corresponding phasors describing their contribution to f of t, 1.01 Hz, 3.749 Hz, pi Hz, etc. So, does this work with any function f of t? How about this function with non-differentiable sharp points? Yes, it is also just a sum of sinusoids. What about non-periodic functions like this guy? Yes, just a bunch of sinusoids. Even discontinuous, non-periodic functions like this one can be represented as an infinite sum of never discontinuous, always periodic sinusoid waves, and that idea forms the basis of Fourier theory. The reason this works, by the way, is that sinusoid functions of different frequencies are mathematically orthogonal to each other, but that's a bit beyond the scope of what I want to get across here. So now, while I've drawn all the actual sinusoids contained in f of t on this grid, remember each sinusoid frequency can be characterized by a single phasor. No need to draw every frequency's entire sinusoid, we'll just show the phasors associated with each frequency. Notice what we've done here. Since every frequency omega has an associated phasor, we've effectively created a new function. For every input frequency omega, it returns the amplitude and phase of that particular frequency. So, instead of drawing a grid of phasors, what I'll do is I'll make a plot where frequency omega is the independent variable, and at each frequency, I'll plot the magnitude of its associated phasor. Just the magnitudes for now. We'll add phase back in a second. I'll call this function big F of omega. Though technically, since I'm not showing the phase information here, this is more precisely the magnitude of big F of omega. Now you can see that each function f of t has its own unique phasor function big F of omega, and you can see that peaks occur wherever those sinusoidal frequencies tend to dominate in f of t. For instance, this f of t plot has a clear sinusoidal component and corresponding peak near that frequency in big F omega. So here's the key question. If you were given a function f of t, could you figure out its phasor function big F of omega? That is, could you somehow determine the phasor associated with every frequency omega such that when you add all the scaled and shifted frequencies together, it will yield f of t? Well, my friends, that is exactly what the Fourier Transform does. The Fourier Transform is a mathematical operation which allows you to represent a function f of t in terms of the different sinusoidal frequencies omega of which that function is composed. That is, you give it a function f of t and it returns the complex function big F of omega specifying the precise phasor associated with every possible sinusoid frequency contained in the function. I really want the connection between these two plots to sink in here. In our big F omega plot, every location on our independent omega axis corresponds to a particular sinusoid of that frequency. So of course, higher or lower omega values correspond to higher or lower sinusoid frequencies. At every frequency omega, we have a corresponding phasor, big F of omega, which multiplies the complex exponential, thereby scaling and shifting its respective sinusoid according to its relative contribution to f of t. If you add together all the scaled and shifted sinusoids as dictated by big F of omega, then ta-da! You get back your original function f of t. Adding all the sinusoids back together is just a simple integral over all omegas. This expression is called the inverse Fourier transform, since it takes in the function big F of omega and returns f of t. Though depending on your units of omega, you may see a constant multiplying the integral to rescale it, but since we're focusing on the concepts here, I'm just going to stick with this definition. So hopefully that intuition is helpful. That's how I most often think of Fourier transforms, and if you have that concept down, I think you're well positioned to understand Fourier transforms in practice. Okay, so what about phase? My Fourier transform plot, big F of omega, currently only shows the phasor magnitudes as a function of omega. Can we somehow also indicate phase as well? Well, what if I did this? I'll add a third axis here and extend my plot into 3 dimensions. Our independent axis denotes our frequency omega, and then I'll use this axis as the real axis and this axis as an imaginary axis. Thus, every frequency omega has its own Argon plane, which can display complete phasor information. Just like before, the location on the omega axis corresponds to a particular sinusoid frequency, omega 0, and carries with it a particular phasor, big F of omega 0, which scales and shifts the sinusoid according to its contribution within f of t. In this example, I have exactly one non-zero phasor in our Fourier space, big F of omega, and thus f of t is a single sinusoid. But of course, a more interesting function, like a decaying exponential, is a sum of many frequencies, each with its own phasor. We'll do a deep dive in the decaying exponential soon. Notice, I've drawn individual phasors here to help solidify this concept, but indeed big F of omega is a continuous function. Now, drawing 3D Fourier transforms like we're doing here is not something you'll see often. After all, the perspective of 3D plots doesn't translate well in flattened 2D textbook figures. So how do we display Fourier transform plots without losing phase information? Well, if I turn the camera around a bit and look at f of omega down the imaginary axis, the perpendicular 2D plane I'm projecting onto is the real and frequency axes. In other words, we're seeing a plot of the real part of our Fourier transform versus omega. Similarly, I can rotate the camera 90 degrees and see the imaginary part of f of omega. What you'll most often see in textbooks is the real and imaginary components of big F of omega plotted together like this. Again, real part in green, imaginary in purple. If phase isn't important to you and you just want to see the relative contributions of each frequency to f of t, you can also display a single plot of the modulus of big F of omega, since this would represent the amplitudes of contributing sinusoidal frequencies in f of t. At this point, you've got to be just dying to see the math connecting the decaying exponential f of t to this strange big F of omega plot I keep showing. If you saw the previous video, you already know the connection, but we'll get there in just a minute. Before we do that, let's test your intuition with a quick Fourier transform example. This function, f of t, is sine of omega 0t. What is the Fourier transform of this sine wave? So remember, the question the Fourier transform is asking is, if I were to make this function by adding together sinusoids, again complex exponentials, what would the amplitudes and phases of every frequency need to be? Pause the video and see if you can come up with an answer. Okay, so let's see here. What frequencies do you see in sine of omega naught t? Hopefully it's somewhat obvious that omega naught should have a non-zero phasor in our Fourier space. I'll draw my phasor as real and imaginary components on our Fourier plot, and also down here I'll show the complex plane representation. Remember, this phasor, big F of omega naught, multiplies the sinusoid e to the I omega naught t, which I'll draw over here. The amplitude of sine is just 1, so perhaps I'll leave the magnitude of the phasor at 1 to start. So, but what would the phase of f of omega naught be? Well, again, sine is a real function. We'll want the real part of omega naught to match if we can. To do this, we'll need to shift the omega naught sinusoid to the right by pi halves, which means our phasor must have a phase of minus pi halves. Okay, so look at that. Now the real part of omega naught lines up with f of t. But f of t doesn't have an imaginary component. So what do we do about that? Is there another frequency in sine of omega naught t we need to include? Yes, there is. Do you know what frequency that is? Yes, it's minus omega naught. Remember, for negative frequencies, the real part lags the imaginary, so if we include minus omega naught and shift it to the right also by pi halves, then the real components add constructively and the imaginary components add destructively. So that's what we need. What would the phasor for minus omega naught be, then? You might think it would be the same phasor for positive omega naught, but in fact, it would have opposite phase. Big F of omega naught is 1/2 e to the minus I pi halves, whereas f of minus omega naught is e to the plus I pi halves. So first, why 1/2 for the amplitude? Well, sine has an amplitude of 1, so each sinusoid's real part must have amplitude of 1/2 so they can constructively sum to 1. So why the positive phase shift for minus omega naught? And the short answer is because the math works, and I encourage you to work out the phasors multiplied by the sinusoids to convince yourself of such. But more conceptually, I tend to think of positive frequencies as progressing forward in time, and negative frequencies as progressing backward in time. Positive phase shifts pull the sinusoid progression backward, since adding phase gives a function a head start, if you will, thus ensuring the same peaks happen earlier in its progression. And negative phase shifts do the opposite. So here would be the Fourier transform of sine, shown on our 3D Fourier plot we introduced a bit ago, and written as a case structure. Have you ever seen sine written in terms of complex exponentials according to this identity? Maybe you'll notice this is simply sine written explicitly as a sum of individual Fourier components, two frequencies, positive and negative, each multiplied by its corresponding phasor. Notice, we didn't do any calculus here, we just used our conceptual knowledge of Fourier theory to come up with a Fourier transform for sine. Perhaps you can come up with the Fourier transform of cosine, following the same reasoning we used here. So you know how we needed both positive and negative frequencies with opposite phase to properly construct sine? You might think that all real functions must have this Fourier transform property. The phasors for the positive frequencies have the exact magnitudes as the negative frequencies, but opposite phases, because only in that way can all the imaginary components exactly cancel each other. You'd be exactly right if you thought that. More mathematically phrased, we'd say that the Fourier transform of a real function must be Hermitian. Big F of negative omega equals the complex conjugate of big F of positive omega. Since real functions contain only one piece of information per input t, and a Fourier transform contains two pieces of information, magnitude and phase, for every omega, it makes sense that this redundancy would exist. Maybe we can use that to our advantage at some point in MRI. We can actually devise a bunch of useful relationships between functions and their Fourier transforms using this property. Real functions have Hermitian Fourier transforms, Hermitian functions have real Fourier transforms. This means even functions have real Fourier transforms, which makes sense since only cosines which are even can add up to produce an even function, and odd functions have imaginary Fourier transforms, since only sines can add to create odd functions. Remember, you might be taking the Fourier transform of a real function, but the Fourier transform doesn't see it that way. The Fourier transform sees a complex function where it so happens that the imaginary component is 0 everywhere. One big caveat to all this before we move on. Technically, the magnitude of our phasors for sine and cosine are infinite. Really quickly, consider the following function g of t. It's 0 everywhere, except between minus 1 over 2a and 1 over 2a, where it has a constant amplitude of a. The area beneath this curve would thus be 1. If we quadruple a, the function is a quarter as wide but 4 times taller, still giving us an area of 1. Imagine we let a go to infinity. Now our function is an infinitely narrow, infinitely high spike, but it still maintains this property that the area underneath it is 1. This is called the Dirac delta distribution. It's not defined as a traditional function, but rather by this property that if you integrate through the spike, you'll get the area underneath. Of course, you can place the spike at whatever time you wish and get a delta of t minus a. Extending this property, we can also see that if we integrate any function f of t times the Dirac delta function, we'll get back the value of f of t at the location of the spike. So technically, this would be the Fourier transform of sine. The phasors are Dirac delta spikes, but still with the phases we found earlier, and areas underneath the spikes of 1/2. So the delta spikes essentially account for the fact that sine and cosine extend infinitely in time. So this is an important mathematical property to point out, but most of the functions we'll deal with in real life are well behaved and have finite Fourier phasors. Would you like to see some of them? Good. Now that you're a Fourier transform expert, there's a few functions in particular which show up over and over in NMR and MRI physics that we should know, so we'll spend some time on those here. We'll look at the decaying exponential, which models our FID decay, and actually any resonance phenomenon, and its Fourier partner, the Lorentzian. We'll look at the square pulse and Sinc function, which are important in excitation profiles and slice selection. We'll briefly look at Gaussians, and then we'll look at the Fourier shift theorem, which allows us to transition between laboratory and rotating frames. If you're just here for a kSpace primer, everything we've done so far should be foundation enough for you to skip to that chapter if you want to, but if you're here for MRI knowledge, these 1D Fourier transform pairs are about to become your new best friends. Let's start with the decaying exponential, which is how we model the free induction decay, or FID, in NMR. We'll write the decay function generally as e to the minus alpha times t, where alpha is a positive real number. We'll consider this function on the interval 0 to infinity, thus defining the beginning of the resonance phenomenon at t equals 0. I encourage you to pause the video and see if you can work the Fourier transform of this function on your own first. Okay, so first we start with the definition of the Fourier transform, integral of f of t times the sinusoid kernel e to the minus I omega t dt. So we'll just plug in f of t and work the calculus. We'll combine the exponents, then we'll undistribute the t. Oh look, this is just an integral of e to the t times a constant. Very easy integral. The constant comes down as a denominator and we evaluate at 0 and infinity. I'll redistribute the t and separate the exponentials here. This makes it easy to see that plugging in infinity will reduce the numerator to 0, thanks to the e to the minus alpha t term. And plugging in 0 for t, we see that the exponentials reduce to 1. So we have 0 minus 1 over minus alpha minus I omega. Distribute the minus sign and we have the solution that the Fourier transform of the decaying exponential is 1 over alpha plus I omega. This is the complex form of what's known as the Lorentzian distribution. Can you picture what this function looks like? Yeah, well, 1 over a complex number isn't something I'm used to thinking about, but a simple trick to use here is to multiply the top and bottom by the complex conjugate of the denominator. A complex number times its complex conjugate is guaranteed to be real, so this allows us to write our function as separate real and imaginary parts. Now it's perhaps a bit easier to see what's going on. The real term has a single peak when omega equals 0 with amplitude 1 over alpha. This is called the absorption Lorentzian. The imaginary part is essentially the same thing but multiplied by minus omega instead of alpha. It looks like this and is called the dispersion Lorentzian. Remember what's going on here. A position on the omega axis corresponds to a particular sinusoid frequency. The real and imaginary values at omega correspond to big F of omega at that location and is the complex phasor, which precisely scales and shifts the sinusoid. Add up all the scaled and shifted sinusoids, i.e. integrate, and you have f of t. Here I'm showing the phasor and scaled and shifted sinusoids for the corresponding frequency in the Lorentzian plot. Notice this particular frequency here. This is omega equals 0. If we plug 0 into our complex exponential, it just becomes 1, and we're left with just big F of omega, which is a complex constant. This is called the DC offset. DC here stands for direct current because this nomenclature comes from electronics. Voltage in direct current does not oscillate like alternating current AC. It is constant. Analogously, the DC offset is effectively just a constant which shifts our entire function f of t up or down the y-axis. Every other frequency omega not equal to 0 would be a form of AC. In this case, our phasor is non-zero real number, so we know on average our function spends most of its time above the x-axis, and indeed it does. Really quick, I'll show you an animation of the inverse Fourier transform of our Lorentzian big f of omega on the right to reveal f of t in the top left. We'll go through each frequency omega one by one and add the scaled and shifted sinusoids, which I'll draw down here, to the f of t plot. This of course would be the integration of our scaled and shifted sinusoids. I'll just show the real part of the Lorentzian, but we'll animate both real and imaginary components of each sinusoid as we add them in. We'll start at omega equals minus 99, whose scaled shifted sinusoid looks like this, and we'll add it in. Then omega equals minus 98, minus 97, so on, and I'll speed it up so we're not sitting here for ages, and hopefully you can see that each frequency addition slowly shapes the integral into f of t. I'll slow the animation down a bit as we get closer to omega equals 0, since these frequencies have higher magnitude phasors and thus contribute more to the shape of f of t. Notice how the DC offset lifts our function up. We'll speed it back up again and look at this. Adding precisely scaled and shifted sinusoids together, we were able to reproduce our function f of t. Well, sort of. It's not perfect, since I only used a frequency range of 200 here, instead of, infinity. But still, I hope that was a helpful visualization. Notice importantly that the imaginary components all summed to 0. So getting back to our NMR application, let's check out the mathematical relationship between f of t and big F of omega. Larger alpha results in a faster decay in f of t and a corresponding increase in the width of the Lorentzian peak. Remember from the previous video that the rate at which the FID decays reflects the amount of time in which spins remain coherent with each other following excitation. We characterize this by a time constant T2, or T2 star when considering field and homogeneity. So you can see alpha here is just 1 over T2. I'll mark T2 on our f of t plot here. Notice that longer T2 has corresponding narrower Lorentzian peaks and shorter T2 has a wider Lorentzian peak. I've animated the Lorentzian here with a plot scale anchored to the height of its peak, but you'll notice from big F of omega that the peak height also changes with changing T2. So here's a fairer animation of the same T2 scaling but with a static plot window. Remember this slide on our last video from spin echoes? Spins which dephase more rapidly obviously have a broader distribution of frequencies. This means you can think of the Lorentzian as a sort of histogram specifying the relative number of spins which have a given omega. Importantly, if the spins dephase very quickly, the resultant Lorentzian is broad and could confound your ability to resolve peaks of nuclei in neighboring Larmor resonances, such as protons in water versus protons in fat. So a couple questions may come to mind as you're thinking about FIDs and Lorentzians. First, why is the distribution Lorentzian? If the spins have frequencies which are randomly distributed about Larmor resonance, wouldn't you expect it to be Gaussian? What would the Fourier transform of a Gaussian be? And why does our Lorentzian function have an imaginary component at all? This of course means that different frequencies have different phases at t equals 0. But wouldn't this imply that following excitation, spins of different frequencies are not all aligned? Also, this decaying exponential is a rotating frame picture, but of course the scanner detects signals in the laboratory frame of reference, which means we'll get a wiggly decay. How might this affect the Fourier transform? You ready for another example? Let's examine the square pulse, which is a common excitation profile in simple NMR circuits. Every textbook has a different name for this function, a top hat, a boxcar, a box pulse, but they're all the same thing. The square pulse is simply a function that is a constant a over some time tau. This is another simple integration, and we'll make the function symmetric about t equals 0 to simplify the math a bit. We're simply integrating a constant times the Fourier kernel over minus tau over 2 to tau over 2, pull the I omega into the denominator, plug in plus and minus tau over 2, and subtract, and we arrive at our solution. Perhaps you recognize this part of the expression from earlier. This is 2 times the sine of omega tau over 2. Plug in sine and we see our function of omega follows a sine of omega tau over 2, all divided by omega. And this is a form of the Sinc function, which in its simplest form is sine of x over x. Here's the square pulse and his Fourier buddy, the Sinc function. These functions show up frequently in NMR, and in the next video we'll see that this is the math which allows us to excite spins within well-defined slices of the body. Importantly, there exists a relationship between the duration of the square pulse and the frequency band of the Sinc pulse, the middle lobe big omega. Tau times big omega is equal to 4 pi. Longer pulse durations will excite a narrower band of frequencies, and short pulses will excite a large band of frequencies. On our last video, we asked the question, how far off of Larmor resonance can your excitation pulse be before you're no longer exciting spins? This is the answer to that question. It depends on the duration of the pulse and thus its frequency content. Note that this relationship works both ways. If you deliver a Sinc pulse to spins, you will excite a square-shaped band of frequencies. More on that on our next adventure. I won't derive this one, but it's important to know the Fourier transform of a Gaussian is a Gaussian. Similar to a square Sinc relationship, a broad Gaussian in the time domain yields a narrow Gaussian in the frequency domain and vice versa. Notice the yellow sigma squared in the expression, which relates to the standard deviation of the time domain function. Okay, finally, consider some function f of t, which is arbitrarily defined here, and its Fourier transform. Imagine we multiply f of t by a sinusoid of frequency omega naught, e to the I omega naught t. What will happen to its Fourier transform? Well, let's see. Yeah, look at that! Multiplying f of t by e to the I omega naught t shifts its entire Fourier transform over by omega naught. Engineers might call the f of t curve the envelope function, which contains a carrier frequency, omega naught. In NMR, we often talk about transitions between the laboratory frame of reference and the rotating frame of reference. So, do you prefer to analyze spins as if you're watching them process from outside the sample, or do you prefer to place yourself in their processing frame of reference and describe their signal dynamics that way? Mathematically, we're just talking about a Fourier shift. In the rotating frame, you prefer to work at omega equals 0. In the laboratory frame, you prefer to work at omega equals omega naught. Electronically, this shift is accomplished through heterodyning, just like a radio. So there's a few Fourier pairs you can keep in your back pocket. Now, NMR and MRI is done with the help of a computer, believe it or not, and if you have ambitions to start analyzing the frequency content of real-life acquired signals from these machines, you'll be moving into the realm of digital signal processing. And there's some intricacies you should be aware of. First, what was a continuous signal has now been digitized. As the signal was delivered to your computer's analog-to-digital converter, or ADC, values were recorded and stored at regular temporal spacings, delta t, where delta t is called the dwell time. The spectrometer operates with a particular sample rate, the number of samples or points it will collect in a given amount of time. And this, of course, is just the inverse of the dwell time. That's not all, though. The ADC does not have an infinite precision and will further cast its measurements into signal amplitude bins. The number of bins available to the ADC is determined by its bit depth. 2 to the number of bits effectively determines the number of available levels. Higher or lower sample rates result in more or fewer acquired points in time. And higher or lower bit depths result in more or less precision in the measured values. Probably the most important consequence of the sample rate is that there is a maximum frequency which the spectrometer can accurately record. Here I have an analog signal which is sampled at regular intervals to yield the yellow plot below. As the input signal frequency increases, eventually we reach a point where the frequency information is lost in the sampled data. And in fact, the sampled data looks as though it were recording a lower frequency than it actually is. This is called aliasing, and it can be avoided by employing the Nyquist criterion. Simply make sure you acquire at least 2 data points per cycle of the highest frequency you want to record. That is, make sure your sample rate is at least twice as high as your maximum frequency. Given a defined sample rate, the maximum frequency which can be recorded unaliased is half of the sample rate and is called the Nyquist frequency. Here's that same animation but with corresponding Fourier transforms. Notice that the yellow plot stops at a lower omega than the upper plot. It simply can't show frequencies higher than the Nyquist frequency. As the analog signal increases in frequency, the discrete Fourier plot reaches Nyquist, then shows alias signal which decreases in frequency. Also, here's the same signal discretization plots from earlier but with their Fourier transforms. Increased sample rate. Notice that this expands our available frequencies in discrete Fourier space. Decreased sample rate. Increased bit depth. Decreased bit depth. Notice the effect the bit depth has on the Fourier space noise floor. And another aliasing animation. Note as well that having a super high bit depth doesn't help you much if you don't properly amplify your signal before it reaches the ADC. If your signal is too weak, then you're not taking advantage of all the bits available to you. And if too high, the signal can only be cast into the highest and lowest bins, resulting in clipping and introduction of unwanted harmonics in your Fourier signal. If you're interested in getting some real-life Fourier transform practice, you can play around with the fast Fourier transform, or FFT as it's known, which is an algorithm that computes discrete Fourier transforms very quickly. It's no exaggeration to say that the FFT was a technological game changer that today exists in nearly every electronic device in some way. As a quick example, let's run an FFT together and see what it looks like. Here's some code you can use. Python on the left, R on the right. Both R and Python are free coding platforms that I use a lot. For this code, I'll create a vector of length 30. First, our independent variable t will be 30 points from 0 to 2 pi, and f will simply be a sine wave. So we can expect one cycle over the range of t. Then we'll simply take the FFT of little f to get big F. Notice the FFT doesn't need the time variable t, only f. All the rest of the code just plots the two vectors little f and big F. So here's our sine vector we generated. Just like we said, one complete cycle and 30 points. So what would the plot of the FFT look like? And here it is. As always, I draw the real components in green and imaginary in purple. These 2 points are our positive and negative frequencies. And all other points have real and imaginary points equal to 0, which is why all the other points are purple. I draw the real parts first and the imaginary parts second, so the imaginary completely cover up the real for all other frequencies. A couple important tips when working with FFTs. First, the number of points in the output will equal the number of points from the input, 30 total in this case. Second, there is a specific order to the returned vector. It goes DC offset, that's the first point here, positive frequencies increasing from left to right, the Nyquist frequency in the middle, and negative frequencies increasing towards 0 from left to right. If you remember our Fourier solution for the sine from earlier, it looked like this. When you take FFTs, it's like taking the negative part of the frequency axis and sticking it on the end of the positive side, where the end is the Nyquist frequency. Finally, there are specific units to frequencies used here. Consider the full range of the input function f. I'll call this the field of view of our input function, perhaps foreshadowing some MRI application later. If the independent axis is time, this would be the duration of the acquisition. If it's space, it would be the full distance we're sampling over, etc. The units of frequency in FFTs is cycles per field of view. The DC offset is 0 cycles per field of view. This frequency is 1 cycle per field of view, and indeed our function contains one full sine wave within the full data range. If little f was acquired in 1 second, then of course this frequency would be 1 cycle per second. The next frequency is 2 cycles per field of view, then 3, and on and on and on. The Nyquist frequency is 15 cycles per field of view, which makes sense. We acquired 30 data points within the field of view, so half of that is the Nyquist frequency. Another way of saying the same thing is that we need a minimum of 2 points per full cycle. Then we have minus 14 cycles per field of view, minus 13, etc., out to minus 1 cycle per field of view. So there's just a few quick tips to help you get started with fast Fourier transforms. Now here's a question which I'll leave to the viewer as an exercise. Can you figure out what the units of amplitude are in the FFT? Perhaps play with the code a bit and see if you can figure it out. Try different frequencies, different numbers of points, different amplitudes, different phases, etc. Try taking the inverse FFT and see if you get back the original function. Oh, and how are FFTs going to be different if you had an even versus an odd number of input points? Okay, and now, kSpace. In my experience, I found that kSpace is somewhat of a conceptual hurdle for those encountering MRI physics for the first time. It sure was for me. I think this happens because many individuals lack the necessary foundation of Fourier theory. But if you followed along with the discussion so far, I'm hoping 2D Fourier transforms feel completely natural. One quick note about variable conventions. So far throughout our discussion, I've used t as our independent variable for f, and omega as our Fourier space variable for frequency. The implication is that t represents time, so a frequency omega must be in inverse units of time. For instance, if t is in seconds, omega would be radians per second, or hertz if you divide by 2 pi. This is simply standard convention in papers and textbooks. Omega represents temporal frequencies in this context. We're about to switch from functions of time to functions of space, images. X, Y, and Z are the variables of choice for 1, 2, and 3-dimensional spaces, and have units of distance such as meters or millimeters. A Fourier transform of a function of space would yield a function of spatial frequencies carrying units of inverse distance, such as radians per meter. For spatial frequencies such as these, we'll use the variable k. And since we're going to jump to 2 dimensions, x and y, we'll need 2 spatial frequency dimensions, kx and ky. So, you remember this animation from a few slides ago. I have a frequency space on the left and I'm marking a particular frequency with a yellow bar which corresponds to a particular sinusoid of that frequency. kSpace works the exact same way, except we now have a 2D plane of possible frequencies kx and ky. Thus our Fourier function is big F of kx and ky. Similar to the 1D case, our location on the kx-ky plane corresponds to a particular 2D sinusoidal frequency. I'll add a grid here to help orient ourselves, and we'll start with our frequency marker at kx equal 2 and ky equal 1. Do you know what the units of kx and ky are? Stick a pin in that. What then would a 2-dimensional sinusoid look like? Well, just like in Fourier space, we give our spatial domain its second independent axis and we'll see. This is a 2D sinusoid, which corresponds to kx equal 2, ky equal 1. It's just a wavy sheet. Or well, 2 wavy sheets, a real one in green and an imaginary one in purple, just like in 1D. Also like 1D sinusoids, our 2D wavy sheets extend infinitely in x and y, though I'm cutting these into tidy squares for display here. The kernel for 2D sinusoids is just the 2 1D kernels multiplied together, e to the I kxx times e to the I kyy, or adding the exponents e to the I kxx plus kyy. You can see from this expression that the 2D function we're describing, f of xy, will increase in phase and thus sinusoidal wiggles according to the sum of phases kxx and kyy. As such, we call these individual 2D sinusoids the spatial frequencies. Low spatial frequencies have few wiggles per unit space, and high spatial frequencies have many wiggles per unit space. Just like we did with 1D sinusoids, I'm going to simplify the plots here by examining only the real part of f to start. And just like in the 1D case, our location in kSpace dictates a certain 2D sinusoid, or spatial frequency, where the progression of phase now has a 2D direction. The higher kx, the more wiggles in the x direction, the higher ky, the more wiggles in the y direction. Also, just like with the 1D case, each point in kSpace contains a complex phasor, which serves the purpose of scaling the amplitude and shifting the phase of our 2D sinusoid. Now let's put this in the context of images. Images are indeed 2D functions of space, f of xy, So instead of visualizing them as these 3D mesh functions, we'll view them as 2D functions of brightness. Large values of f are colored white, low values colored black, a standard linear grayscale. Here's the same animation showing our walk around kSpace and corresponding spatial frequency at each kSpace location. And here's the same animation of our phasor scaling and shifting the 2D sinusoid. Notice that when the phasor amplitude is low, the sinusoid stripe pattern becomes less pronounced. This is because the amplitude is lower, and so the range of brightness values spans a smaller portion of our grayscale. Finally, just like with our 1D functions, our image f of xy is the element-wise sum of all the scaled and shifted 2D sinusoids dictated by our kSpace phasor function. Let's say we add another frequency to our kSpace plot. How about kx equal 1, ky equal 3 with phasor 2 minus I? That spatial frequency looks like this, and when summed into f of xy, our resultant image looks like this. If we add all the spatial frequencies together, each one precisely scaled and shifted according to their corresponding kSpace phasors, we produce our full image f of xy. Mathematically, this process of adding all the scaled shifted sinusoids together is just like the 1D case, except it's a double integral over kx and ky. Isn't that neat? Now you might notice a few things here. First, the frequencies near the center of kSpace seem to have larger phasors than those near the edge. In fact, the very center frequency at kx equals 0, ky equals 0 is off the chart here. This frequency in particular is the DC offset, and for images is generally orders of magnitude higher than most of the other frequencies. Since pixel values of images are all higher than 0, the entire image rests at an average pixel value much greater than 0. You might also question why I've chosen to use only integer multiples of kx and ky. Well, indeed, if f of xy is continuous and infinite, then kSpace will also be continuous and infinite. Since our discussion is focused on images, discrete functions of space, kSpace will in turn be a discrete function of spatial frequencies. Also, Nintendo sprites are great to use for kSpace demonstrations since a clear image can be recognized with very few pixels. Now, just like we did in image space, I'm going to turn our kSpace camera around so we take a top-down view. This way we'll see kSpace as a 2D map. I'll play the same animation of building Mario one frequency at a time. In this view, kSpace is shown as a grayscale image where the brightness of a voxel corresponds to that phasor's magnitude. And this is most often how you'll see kSpace represented in textbooks and papers, a magnitude image of the complex Fourier transform. Actually, for display, the logarithm or fractional root of the magnitude might be performed first, otherwise all the frequencies would be dwarfed in brightness by the DC offset. Phase is generally ignored in these displays. If you wanted, you could color the points according to the respective phases, perhaps with a cyclical color scale, but little information is gained in doing this, except in really cool MRI sequences which are designed to leverage the extra information phase can provide. More on that in a later lecture. And now I'd like to pose a few questions to help you understand some of the details of kSpace better. First, I'll pick a location in kSpace at random. Say this point here, kx equal minus 3, ky equal 2. Its corresponding sinusoid looks like this. Now how can you tell the sinusoid pattern from the kSpace location? Well, the way I think of it is by looking at a vector from the kSpace origin to the point of interest. The length of the vector reflects the spatial frequency or number of cycles per distance, and the direction of the vector corresponds to the direction of the fringe progression. Another way to think of it is to see that if we examine any single row of pixels, the frequency will be the kx frequency, and any single column of pixels will be the ky frequency. Here, as I walk through kSpace, you can see how the spatial frequency changes in this regard. But wait a minute. We're at point minus 3, 2 in kSpace here. But let's say I go to the point 3 minus 2. Just reverse the frequency signs. What would that sinusoid look like? It looks exactly the same. And that's true for all reversed pairs of points in kSpace. So wait, is it possible to tell these spatial frequencies apart in an image? And if not, does that mean that kSpace is redundant? The same information appears twice? Well, remember, the images I'm showing on the right here are the real parts of the sinusoids which are in fact complex. There is an imaginary part too. Here's the two sinusoids of reversed frequencies showing both real and imaginary parts, in green and purple respectively. The top sinusoid progresses in this direction since real leads imaginary in this way, and vice versa for the bottom. Remember when we took the Fourier transform of sine a bit ago, we found that for an entirely real function the Fourier transform must be symmetric about k0 because necessarily the imaginary components must add to 0. Same thing here. K-space of real functions is Hermitian. If the image is entirely real, necessarily reflected positive and negative frequency components will sort of counter-mirror each other. They are each other's complex conjugates. Check out Mario's kSpace again, and you see that every point's magnitude is equal to his buddy mirrored across the origin. So does this mean that half of the kSpace information is redundant if the image is real? Actually, yes. And in fact, for many MRI sequences, you can speed up your acquisition by only acquiring half or more of kSpace. Notice how I can zero fill the entire bottom half of Mario's kSpace and the image still has reasonable contrast. Look at all the cool tricks you can do when you know the math. Now the center of kSpace contains low frequency sinusoids, and thus information regarding gradual changes in intensity are largely contained here. Conversely, the high frequency information closer to the Nyquist edges forms the sharper changes in intensity and are thus more responsible for fine details within the image. In an image you can see that if we remove high frequency information of kSpace, the image lacks fine detail, but gradual variations are maintained. Conversely, if we remove the low frequencies near the center of kSpace, the image lacks signal and contrast, but the fine details remain. These would be low and high pass filters, respectively. Now perhaps we should return to the question, what are the units of kSpace frequencies and how do they relate to images? Well, just like in the 1D discrete Fourier transform, the number of pixels in the image is the same as the number of points in discrete kSpace. Also, in the discrete Fourier transform, discrete kSpace frequencies have units of cycles per field of view. And now perhaps it makes some sense why I picked this nomenclature earlier. The image has specific dimensions in x and y corresponding to physical distances, which our image covers, our fields of view, in x and y. Moving from DC over to the right by 1 unit gives a sinusoid frequency kx equal 1 cycle per field of view in x. If, for example, the image is 10 centimeters wide in x, this would be 1 cycle per 10 centimeters or 10 cycles per meter. Move 1 more unit and we're at 2 cycles per field of view. And so on until we reach the Nyquist border. What's our frequency here? Remember that in discrete Fourier space, all of our spatial frequencies are being cast into a discrete collection of pixels. The Nyquist frequency, the largest frequency we can display in this discrete image without aliasing, is half of the sampling frequency. In this case, our image is a sampling of data with n sub x pixels or n sub x points per field of view in x. That is, we need 1 sinusoid cycle to extend across no fewer than 2 pixels, a crest and trough for each pixel. Thus, the Nyquist frequency is n sub x over 2 cycles per field of view. For example, if each pixel in our image is 1 millimeter wide in x, and the x field of view is 10 centimeters, there would be 100 pixels across the image, and thus the Nyquist frequency would be 100 over 2, or 50 cycles per 10 centimeters, or 500 cycles per meter. A big take-home from this is that the step size in kSpace dictates our field of view, or equivalently, the field of view you choose for your image dictates the kSpace step size. Also, the size of your kSpace array, i.e. the locations of your Nyquist borders, dictate the image resolution or pixel size. Or again, the resolution you choose in your image dictates the size of your kSpace array. The same relationships hold for the y direction as well. Moving up in ky gives you units of cycles per field of view in y. Notice in this animation I have fewer cycles or fringes in my ky Nyquist frequency than I did for the kx Nyquist. What does that tell you about the image? If the ky and kx Nyquist frequencies are different, that means your pixels are not isotropic. They're rectangles, not squares. Remember that the Nyquist tells you your resolution. If your resolution is different in x and y, then the Nyquist in x and y will be different. Here's an example of the NES Mario sprite. The pixels here are isotropic squares, but the fields of view are different in x and y. So since the pixels are isotropic squares, the kx and ky Nyquist frequencies will be the same, and will have a square bound to kSpace. But since the fields of view are different, we know the step sizes in kx and ky will be different. But as always, the matrix size, the number of rows and columns, will be the same as in the image. So I hope that's a helpful way of visualizing kSpace in step with image space. And we've been illustrating kSpace on a 2D Cartesian grid with the DC offset at the center, that is, kx equals 0, ky equals 0 at the origin. Appropriately, we call this a DC-centered view of kSpace. Well, if you want to play around with the fast Fourier transform in code, just like with the 1D functions, there is a particular organization to the 2D discrete Fourier transform you'll get back. If you think of our kSpace in standard 4-quadrant layout here, 1, 2, 3, 4, the data organization you'll be given from a fast Fourier transform of an image will look like this. The DC offset is at row 1, column 1, and the quadrants are in these positions with these signs for kx and ky. Kx equals 0 is column 1 of the matrix, and ky equals 0 is row 1 of the matrix. And now the Nyquist frequencies are in the middle. Since x and y coordinates translate to matrix columns and rows respectively, this is how I think of the respective spatial frequencies. For example, the first row second column of kSpace, P1, would encode for this spatial frequency. Since the imaginary part lags the real and increasing column number, I think of this as a positive frequency in x. Point P2 here, which is at kSpace row 2, column 1, would correspond to this spatial frequency, where imaginary lags real in the downward direction, which I think of as progressing in the negative y direction, although it would be increasing in row number. Others may visualize kSpace with different correspondences between x, y, row column, positive, negative, and that's fine. If it makes sense to you and you can work with it, you're good. This is just the organization that I have in mind. So there you have it. A quick, yes, that was quick, intro to Fourier theory in kSpace. So where are we going with this? Well, in fact, an MRI scanner collects its data in kSpace. As a quick teaser for our next adventure, consider a 2D distribution of spins following excitation by an RF pulse into the rotating frame. So the z-axis here is coming out of the screen. Imagine we deliver a magnetic field gradient to these spins, let's say in the y direction. Spins near the top now experience a higher magnetic field, and spins at the bottom a lower magnetic field. So what happens? Well, the individual spins will accumulate phase according to their location within the gradient. Red spins gain phase, blue spins lose phase. And then we turn the gradient off. Do you see it? Imagine we deliver a second gradient, this time in the x direction. Same deal. Spins gain phase according to their position in the gradient. And then we turn it off. Do you see it now? We're creating our own spatial frequency within our spin sample. You recognize this as a 2D sinusoid kernel corresponding to a particular location in kSpace. Thus, we are encoding our spins in kSpace using these gradients. If you were to calculate the vector sum of all these encoded spin magnetic moments, the resultant vector is in fact the complex phasor corresponding to that location in kSpace. And that is where we'll pick up next time in our discussion of the gradient echo pulse sequence. Until then,